Hello! Today we're going to look at the Moivre and Stirling approximation, better known as just the Stirling approximation. And we're going to use this approximation to find some approximations for summations and integrals. There will be a lot of approximating. But first let's look at which approximations we'll use. Now there are many approximations and you can actually have a Stirling series, but here we use the first order as second order as it were to find interesting approximations for sums. Now as it will turn out, you can actually fit a lot of approximations inside of a Stirling approximation. Firstly, we're going to rearrange this approximation so that we have four unique arrangements. Firstly, we'll use the first approximation, which is that n factorial divided by n to the power n is approximately e to the power minus n, or rather, for a more accurate approximation, n factorial over n to the power n plus a half is approximately 2 pi times e to the power minus n. The first thing that we're going to do is to put a summation around both and then sum over n. Now here we summate from a until infinity. We also integrated a x to the power n, and we also did that on the other side, and as long as the absolute value of x is smaller than e, we actually have on the right side a geometrical series. And a geometrical series we can actually rather easily solve for. And now on the right hand side, on the end, we have actually a compact version, a compact value, which gives an approximation for the values on the total left side, which would be very hard to calculate. So instead of having to compute an infinite amount of terms to find a really good approximation, we actually can just use this approximation on the right side, which is way easier to compute. What we also have is that if you want to sum from 0 until infinity, you can just take the first few terms for the real value of the sum, the real value, the real formulation, and then for higher terms where you have a larger value of n, you can actually use this approximation, as the approximation only gets better for higher values of n. But don't use it for low values of n, it's rubbish. Now we can not only sum over it, but also integrate. And if you solve this integral, you get what you have on the right hand side, and this is a good approximation for the left hand side for higher values of n again. Now we take the more advanced approximation and actually do something very similar as we just looked at. So I don't have to explain this much, but just the term of the square root 2 pi carries over, and the summation is a little bit different because instead of n to the power n, we have n to the power n plus a half. Similarly, we can also do the integral, and here we have the same idea, but just a different approximation for a different summation, or rather for a different integral, although they are very alike. Now here we do something smart. We actually take the n to the power n plus a half and take that half out of it, and then have the square root of 2 pi n times e to the power minus n. Now this is a very interesting approximation for integration, because if you integrate from 0 until infinity with a substitution, you can actually get a Gaussian. And the Gaussian function is something we can integrate over from 0 till infinity. And as this is a better approximation, a better Stirling approximation, it also better approximates the integral from n factorial over n to the power n from 0 to infinity. Now, of course, here we do have the trouble that we can't set a limit to an arbitrary value, but have to do 0 for the beginning. And this is a little bit problematic because the value is very rubbish for low values. So what you actually have to do is to use a numerical approximation of the area for both the integrals for lower values and then correct for this. But even so, it is a really good approximation for higher values. Now it turns out that you can actually also integrate an x to the power n inside of there. It just requires some substitutions, which I didn't do, but I knew you could probably do so. And I would like to use, and I would like to thank Wolfram Alpha for actually allowing me to find this integral. I think it's a really neat approximation and gives you some flexibility. And hopefully you can actually do something with this. Now we're going to look at the second approximation, where we approximate 1 over n to the power n with various terms, and also 1 over n to the power n plus a half with various terms. Now firstly, we can just use summation again, and we also use here x to the power n to give us more flexibility. And it turns out that if we do 0 to infinity, then we actually get e to the power x over e. And this, of course, is rather curious. Like, we've never really seen something similar in mathematics. I don't think so, where you have a radical for e to the power 1 over e. That's rather strange. But at least, but yeah, this is turns out to be the case, and it's rather unheard of. I think. Okay, so here we're going to have an approximation for 1 over n to the power n. And if you look at the summations which we first have, we also plug in x to the power n to have some flexibility. And on the right hand side, you actually get the exponential function of x divided by e. Now, as some of you might be familiar with, if you use x is equal to 1 or x is equal to minus 1, this gives us the famous 7 more dreams summations. And now we can actually find a first order approximation for these values. And if you'd like, you can also make a first approximation for the even terms and the odd terms by smartly subtracting or additioning these terms. Now, this of course is great, and you don't want to use this exact value as an approximation, but again, you can replace some terms to actually get the lower values of n to be correct, and then for the higher values of n, you actually do an approximation. Now, similarly, you can also do this again for 1 over n to the power n plus a half, and then we have this summation. This is also an interesting one, and is actually quite similar to what we just saw. Now, we can also combine this and actually have something which I would like to call Savarmore's Euphoria, where we have all these kinds of summations of odd parts, of even parts, where we have an integer plus a half for the exponential. And this is really interesting. And if you add these terms, you get an interesting combination. Of course, you still have to adjust for this to have some correction terms for lower values of n. But overall, this result is actually really interesting and might help to develop a better approximation for these summations and to make more educated guesses about values for other applications in mathematics. Now, with that, I would like to thank you for watching. Please keep in mind that for low values of n, this is a terrible approximation. So you always have to replace some lower values of n to get a good approximation. But I do think this is actually rather useful, also for physical applications or just approximations to get a better value. It should be noted that everything I have made here is original content. I don't think anyone has found this yet. I did post this already on Reddit, but So if you think you've seen it already, it might be on there. If someone already found this out, please do tell me, then I will give them the credits. Um, if you find me another approximation, please do let me know. It might well be possible that I've missed one. I also would like to state that I hardly make any videos on this channel. I rather would only make original content here instead of doing a tutorial, something similar. I do really like mathematics, but I don't see the point in actually giving a presentation of which are already many online. It will not add any value, and I think presentations in which I show you mathematics, which I do believe are original, do add value. And with that, if you would like to see future videos, because YouTube's not uh, that much a fan of channels which have a low production rate of videos, please do hit the bell button so that you will be notified when I actually once in a year create a video. And with that, I would like to thank you for watching and have a good one out there.